Okay, hello everyone, this is Yiwen. Today I'm going to introduce our paper, Insecurity of Operational Cellular IoT Service, New Vulnerabilities, Attacks, and Countermeasures. Cellular IoT service connect the IoT device over the cellular network. More than 150 cellular networks worldwide have rolled out massive IoT service, such as smart metering and environmental monitoring. Such services share the existing cellular network architecture with the non-IoT ones. So to support massive IoT devices that focus on low cost, low energy, and small data volumes, two cellular network technologies has been proposed. One is LTE-M that supports the data, text services, and voice. Then the other is NB-IoT that supports the data service only. They can extend the battery life of the cellular IoT device while reducing the modem complexity. Here, there are two major IoT-specific functions supported by both LTE-M and NB-IoT. The first is half-duplex communication, where an LTE device cannot transmit and receive the data simultaneously. So it causes the maximal downlink speed of the LTE-M and the NB-IoT are only 300 kbps and 26 kbps respectively. The second is the power saving mode. It allows an IoT device to enter a sleep mode to save the power. The sleeping time ranges from 4 hours to 413 days. And there are three limited size of the active time. Different from conventional cellular device, which only have two operational modes, the active mode for immediate message transmission and the inactive mode for waking up periodically to check the paged message. The cellular IoT device have three operational modes, active, inactive, and the sleeping mode. The device in the sleeping mode has no radio connection and will not respond to the pager message. Specifically, a sleeping IoT device is unreachable, but it keeps registration state and IP with the core network. As I mentioned in the previous slides, standard regulate the minimal sleeping time for a device is 4 hours. So most of non-IoT devices will not enable the power saving mode, since it will cause them missing all the incoming call, text, and data. Then in practice, most massive cellular IoT users demand only small data volumes. So the carrier provides them with service plans that have lower start price, but higher unit rates. Moreover, the cellular IoT users need to pay for each text message. But for the non-IoT users in the US, most of them usually do not need to pay for the text while they having a data service plan. So at first glance, cellular IoT users are more vulnerable to spamming attack. However, it is challenging to distinguish their IP addresses and the phone numbers from the non-IoT ones, considering the following reasons. First, the carrier network does not adopt different IP assignment mechanisms for cellular IoT and the non-IoT device. So no difference can be observed from their IP addresses. Second, an IP addresses may also be used by other kind of IoT device, like the Wi-Fi IoT via the operator's trust non-3GPP accessed network. So profiling IoT traffic may not be able to clearly differentiate those cellular IoT devices from the other IoT ones. To launch text spamming attack, identifying the IoT's phone number is also a challenge. Since the number assigned to the cellular IoT and the non-IoT users usually follow the same format, and the carriers do not adopt any different assignment policies for the IoT and the non-IoT phone numbers. So in this work, we discover 5 vulnerabilities from operational cellular IoT data and text service. By exploring them, the adversary can identify the IP addresses and the phone numbers from used by the cellular IoT users to even launch unaware spamming attacks. Now let's see the first vulnerability. It comes from the inconsistent state between the transport layer communication and the underlying power saving mode at the cellular IoT device. So it allows the adversary to remotely probe whether an IP address is used by a cellular IoT device. As I introduced in the previous slides, most of cellular IoT devices enable the power saving mode to extend their battery life, but the other cellular device not. So once there is a kind of probing packet to which each non-sleeping device has to reply, that means no reply from that device implies that it is offline or sleeping with the power saving mode. Here, the offline case can be excluded since the probing is only triggered at the observation of there is traffic coming from that IP address. Besides, recent studies show that the top 2 IoT communication protocols are both TCP-based. Then, according to our observation on the cellular IoT device with us, the TCP connection between each device and its server keeps staying alive, whether the device is sleeping or not. Therefore, the prober can leverage the active TCP connection with the IoT server for probing. So here, what kind of TCP packets can be used for probing to make all the active device reply, but does not affect their ongoing TCP connections? We discovered that one kind of TCP ACK packet is suitable. This TCP ACK packet acknowledges the sequence number that has not been used by the other TCP connection end. Besides, based on an RFC document, while receiving such ACK packets, the receiver needs to reply to it with another ACK packet using a correct sequence number, and then discuss the original one. So it does not affect the state of the ongoing TCP connections. Then how to make sure that at least one probe can be proceed while the probe device is sleeping for a TSM-enabled cellular IoT device? According to a study, most device vendors restrict the active times for a longer battery life. So 80% of massive cellular IoT devices are with average active times less than 5 minutes. Therefore, the prober can send 6 probing messages with 5 different intervals to the connection source IP. We validated the effectiveness of our probing mechanisms by examining whether it can successfully identify the IP addresses used by those PSM-enabled cellular IoT devices. Here, we conduct the experiment using 13 text devices in our campus network. It includes 7 cellular IoT devices, 2 Wi-Fi IoT devices, and 4 smartphones. The PSM is enabled on 5 cellular IoT, and the length of their active times are randomly set to the available values between 6 seconds and 5 minutes. As shown in this table, the prober can accurately identify 5 PSM-enabled cellular IoT devices with 100% accuracy. However, the probing cost varies with different devices. The PSM-enabled cellular IoT device takes much shorter time, which are around 2 minutes, than the other devices do, which are around 10 minutes. The reason is that the former device can be identified once a probing message being sent while they are sleeping, but the later device cannot stop until all the probing messages are sent. So we further adopt a rate-based screening mechanism to reduce the cost of probing. As I introduced in the background, the maximal downlink rates of the LTM and NB-IoT device are limited to 300 kbps and 26 kbps respectively. So our pobber can record the downlink traffic statics for each IP addresses whenever any downlink traffic is observed, and keep calculating the downlink rates over time. If any peak downlink rates is observed for an IP address to be higher than the 300 kbps within a minute, this device can be inferred as non-IoT. As shown in the right figures, we tested the peak downlink rates of 2 non-IoT devices in various scenarios with a total of 640 measurements. It is observed that only 5 measurements, which takes only 0.78% of the total, have peak downlink rates lower than 300 kbps, and they are collected in the near dead zone case. Then the V2 is spammy traffic sent to a sleeping cellular IoT device can be accepted and charged at the core network, but the sleeping device is unaware of it and cannot take any immediate defense. Here, the root cause is current network operations for non-IoT devices are directly applied to the PSM-enabled cellular IoT without any modification. We can see from these 3 figures, the downlink deliver is available even when non-IoT devices are in inactive mode. Since when downlink packets arrives at the gateways will send a notification to the MME, and the MME's pager message will notify this non-IoT device to receive the data. So the P gateway can charge this downlink packets for non-IoT device. However, it may cause charging issues to those sleeping IoT devices because the sleeping IoT devices are charged for the incoming downlink packets without receiving them. Moreover, if the incoming downlink packets are spamming, the sleeping IoT device cannot take any immediate defense against them. The third vulnerability is most IoT numbers only have the text service, but do not subscribe to the voice service, while those non-IoT numbers always have. So it may cause different call response time while calling an IoT and a non-IoT number, which can result in the leakage of phone number device types. We can see in the right figures, when a VoLTE user makes a phone call to a phone number, the user can receive the session progress or reading message from the VoLTE server. However, the call response time in case 1, where the call-in number is for an IoT without voice service, is much shorter than in case 2, where the number is a non-IoT one. Because in the formal case, the VoLTE server does not need to send the invite to the call-in and wait for its response. We validate this vulnerability by considering 3 IoT numbers for non-IoT ones and the 2 unassigned ones from carrier US2. Here, we consider the call-ins in various scenarios with different voice technologies, including 3G, 4G CS4 back, VoLTE, and voice over Wi-Fi, with different signal strengths and power status. We can see in the bar figure the values obtained from calling the non-IoT and IoT number can be clearly differentiated. Specifically, the minimal value from the non-IoT number are still 0.67 seconds higher than the maximal value from the IoT numbers. However, the values from the IoT numbers are comparable to those from the unassigned numbers with similar median value around 0.74 seconds. Therefore, it can be exploited to differentiate those non-IoT numbers from IoT and the unassigned numbers. Then we further discovered the V4 that the short message signaling gives different response while sending to IoT and the unassigned numbers. We can see from these 2 figures, the response message include a delivery report shows delivered for an IoT number, while it indicates an error that occurs the request facility not implemented for an unassigned number. So it can be used to differentiate the IoT number from those unassigned numbers. The last vulnerability is that we find some carriers charge the cellular IoT users for both outgoing and incoming text message. Here, not all carriers provide IoT users with security mechanisms against the malicious sender. Therefore, once an IoT number is identified by the adversary, the owner will suffer from the serious spamming attack. For the proof of concept attacks, we devised a data spamming attack against cellular IoT device by leverage the V1 and V2 and then evaluate its damage. We find the IoT device do not receive any spamming traffic, but they are charged for it. Then for the TCP spamming, US1 and US2 impose charging volume caps, 200 KB and 545 KB respectively. But the US3 has a higher cap with around 10 MB. For the UDP spamming, US1 do not impose any charging volume caps, which can achieve up to 16 MB, while the US2 and 3 have charging caps about 7 MB and 10 MB respectively. So the IoT data spamming attack can lead two kinds of damage on the IoT users: excess bills and the denial of IoT service. We next devised an IoT text spamming attack based on V3, 4, and 5. We can accurately identify the IoT numbers from 7 non-IoT ones. We send the text spamming to the victim device at different rate, and all messages were received and charged. The US2 charges IoT user with 5 cents per text, which means the adversary may increase the victim's month bill by $5 per second if auto-renew is enabled. At last, we propose a suite of solutions to address the above 5 identified vulnerabilities. We introduced a vertical security miner to address the V1 that the device should terminate all outgoing connections before entering the power saving mode. And a horizontal security miner was proposed to address V2. An additional time delay is introduced to the call response time to prevent V3, and the SM center should provide a general error code information to prevent V4. At last, the carrier should impose the restrictions on the pushed text service to prevent V5. So in conclusion, we identify and validate 5 vulnerabilities of the cellular IoT. We devised 2 proof of concept attacks and assess their real-world impact on 3 major US operators. We propose a suite of standard compliant solutions, and all findings has been reported to the relevant operators. So thanks for your interest. We welcome to any questions and suggestions.